All right, everyone, it is 10 past the hour and we are live, so let's get started. First off, I'd like to thank everyone again for joining us at TMLS 2021. Before I introduce our next speaker, I'd like to just go through a quick reminder to check out our sponsor booth, which you can navigate to on our left, on the booth button. Once you're there, you could enter to win some pretty cool swag, including a custom pair of Nike. Now, without further ado, I'd like to introduce our next speaker, Douglas Sherk. Doug is currently building an end-to-end ML platform for computer vision edge devices at Axon, maker of the Taser stun gun. Doug was formerly the CTO of Passenger AI, which was acquired by Zippin Inc. There, he led a team of engineers developing self-driving car interior monitoring solutions that were sold to Fortune 20 companies. Doug lives in the San Francisco Bay Area for several years, where he worked as a software engineer at companies like Mozilla and Zynga. He has a Master's of Science in Computer Science and with a Machine Learning Specialization at Georgia Tech and a Bachelor's of Science in Mechatronics Engineering at the University of Waterloo. Doug will be giving us a talk on scaling deep learning model training. Please give a warm welcome in chat.
Thank you, Peter. Appreciate it. All right, let me just get up my screen going, and then we will get started. Okay, can everyone see this? All right, let's get started. So I'm going to be talking about scaling deep learning model training. So Axon is a company that's behind the Taser stun gun. And we have a wide range of products, including the Taser and several others like the Axon body and stuff like that. So the police officer here is currently carrying that Taser and the Axon body. And one of the other products that we've been working on is called the Axon Fleet. And that now has automatic license plate recognition functionality in it, and that's on the market right now. So I'm going to be talking about some of the techniques that we use to scale up our deep learning model training for that product and beyond that as well. So a lot of people are training models now, usually on a single machine, and usually with one, maybe a few GPUs on that machine. But we're going to be talking about something really cool, which is scaling up that training to many, many GPUs. So the basic problem that we're going to focus on is this. So let's suppose that you're trying to train your model and it's taking days and you want to knock that down. You want your training to be a lot faster. So this talk is going to be focused around that question and answering that. And I'm going to describe a three-step process that you can use to address that. So the first is switching to platform-agnostic training. And that's probably the least intuitive of the three. And I'll get into why that's important. So the basic approach there is that you're going to port your model to like a PyTorch Lightning or similar thing for TensorFlow like that. And what that'll do is it'll make it platform agnostic, so you can train it on CPU, GPU, any number of GPUs, et cetera. And then the advantage of that is that it'll make the distributed computation almost free. Like you won't have to do anything beyond that to make it suddenly work on a cluster of nodes. The next step would be the actual distributed training itself. So wrapping up your training script and putting it onto a cloud platform. And then you can like fan it out horizontally. And then the last step would be to tune your compute config to be optimal for your model and whatever settings you're using there. So I'll describe each of these step by step in different sections of this talk. So I'm going to be focused mostly on ML practitioners. So if you're doing like engineering, this will be most applicable to you. And it's really applicable just to deep learning models, especially heavier ones for computer vision, NLP, and tasks like that. It's going to be mostly applicable if you're using non-trivial data sets. So if you're using very small data sets, it doesn't make sense really to fan out, and I'll explain why later. And you also have to have a pretty significant training budget. Last is we're going to be very PyTorch focused, but a lot of these principles are very widely applicable and not just for PyTorch. Okay, so let's get into it. So the three-step process was platform agnostic training, distributed training, and then tuning your compute config. So first step, platform agnostic training. So the reason you do this, again, this is probably the least intuitive of the three. The reason you do this is because if you can get your training working on both a CPU and one GPU with PyTorch Lightning or a tool like it, then it becomes very easy to distribute it. It's just like the idea that getting something working with like one or two things makes it so that you can generally get it working on like 4 or 8 or 16, et cetera. So the first step is going to be porting your training code over to PyTorch Lightning. And then once you're there, doing the distributed training is basically free. So if you're writing raw PyTorch code, you have to do all sorts of like if statements, checking for distributed data parallel, distributed sampler, all sorts of stuff like that, checking for the rank of the node. But if you're doing it using PyTorch Lightning, it abstracts all of that away for you basically for free. So I'm not going to spend a lot of time on PyTorch Lightning and what exactly it does. You can read more about it on pytorchlightning.ai. But just very quickly to explain the magic behind it. On the left here, you can see some training code that is not using PyTorch Lightning. And as you can see, it's very imperative, meaning that you're just sort of calling things step by step. You know, you're instantiating your model and the layers in it and everything. Then you have like a check for if you're on rank 0, which basically means the master node of your cluster, etc. So you're just doing things sort of step by step. And then you have to have a lot of if statements, like you can see here with the global rank equals 0. But then when you switch to PyTorch Lightning, basically what you're doing is you're taking out each of those independent blocks and refactoring them such that there's like one method that does one exact function. So for example, here you have your initializer here, which defines all of your layers. Then you have your forward pass, which is here too. And what that does is it's exactly what it sounds like. Given an input data point, it returns the output, and it's expected to implement all of that for you. And then your optimizer setup. And there's much more, but the basic idea is that if you group your functionality like this in the way that PyTorch Lightning expects, it can basically do all the magic for you of making it work in a distributed setting too. So you don't have to do anything to make that happen. It does it automatically. Once your code is all wrapped like that, then all you have to do is a simple training command like this, where you instantiate your model and a trainer with whatever number of GPUs, and then you tell it to fit to your data set. And then once you're there, it becomes effectively platform agnostic, as we were talking about. So you can, for example, if you want to train on a single node with just a CPU, then you just specify no GPUs. Single GPU would be 1 GPU, etc. And then to go to multi-node, which I'll explain what that means in case anyone here is not familiar with that, all you have to do is specify the number of nodes. So there's like no if statements to check, are you in distributed, are you on a single node, etc. It just becomes absolute magic like that. Okay, so let's get into the meat of this talk now. So now that you're platform agnostic, you can do a lot. So let's talk about distributed training itself, and we'll go over some nomenclature first. So for starters, the GPU is sort of the elementary unit of work division. So basically what that means is like, it's the foundational building block that you're going to assign a task to. If you think of like a worker queue or something like that, then your GPU is basically that. It's like the fundamental unit that can compute for you. Then there's your node, which is basically a machine, and a machine can have multiple GPUs. Then last is a cluster, which is many nodes. So a cluster can have nodes, a node can have GPUs. Another important term to understand is like world, global, total, effective. They all more or less mean the same thing, but it basically means across an entire cluster, how many of something is there. So for example, the world size is the number of GPUs in the cluster. So a couple more terms. So parallelism, how do we actually parallelize our data, and how do we parallelize our training to take advantage of being on a cluster? The basic idea is that there's two ways to do this. One is not very popular anymore. The other is much more popular. So model parallelism, the idea behind that is that you're actually breaking apart your model and taking one part of it and putting it on one node or one GPU, and then taking another part and running that on another GPU. That used to be popular in the early days of deep learning, but it's not too popular now, although there are still use cases for it. It's just that at the scale of most people here, that's probably not going to be very useful. But then there's data parallelism, which is when every GPU has its own version of your model. And then all you're doing is taking subsets of the data and training the model on each GPU on that subset, and then shuffling at each epoch or by some other cadence like that. So with this sort of setup, you end up with multiple configurations. So you can have a single node and a single GPU, which is just like one machine with one GPU on it, a single node with multiple GPUs, which is also exactly what it sounds like, and then multiple nodes and multiple GPUs. So on the right here, we've got a diagram showing that. So in this case, we've got 4 GPUs per node. So we've got 2 nodes. And then our overall world size, so coming back here to this term, the world. So our world size, which is the total number of GPUs in the cluster, would be 8, because there are 2 nodes and 4 GPUs on each node. On the left here is a simple illustration of data parallelism. So if you were on a single node, this is what you would do. You'd have your data set, you'd pass it through your model, do all your backprop and everything, and you're good to go. In your distributed setting with data parallelism, what you would do instead is you'd have multiple workers, and they would each get a subset of the data. So in this illustration, one batch of the data or one subset of the data goes to the first worker, and the other subset goes to the other. So that's the basic idea, and that's how you get a lot of the benefits from that. And you do that because the data is not all going to fit on one node, basically. Like a single GPU is not going to be able to fit all your data, so you can take advantage of the scale. And on the right here is how most systems these days actually do that parallelism and how they train on these multiple nodes and then reconcile them. So the basic idea is that there's this algorithm called ring all reduce. And what each of the workers does is they train on that subset of the data that they get. They do their backprop and they get their gradients, and then they pass it on to the next worker. So the more intuitive way that you might think is to have like a master node, but that introduces a communication bottleneck. So it means that you don't scale as well as you could. But the ring all reduce more or less removes that communication bottleneck, and it makes it so that we can get almost linear speed up. Meaning if we add X more compute, we get like X more speed out of it. So here's what you can more or less expect when you actually do distributed training. So it costs more per hour, right? Because if you're training on 2 nodes instead of 1, it's going to cost more. That makes sense. But it trains faster, right? So if it takes half the time to get there, but twice as much money per hour, then you actually end up pretty much at a wash. The speed up, though, isn't quite linear. So as you can see on the table down here, this is an example of an expected scale up where you go from 1 to 2 to 4 nodes training. And then at like, $9.10 per hour per node, we assume that you don't get a perfect speed up. So if this was a perfect 2x speed up from 1 minute, 30 seconds to 45, that would be exactly 2x. But we're not getting a perfect speed up, we're getting slightly suboptimal. So ultimately the cost per epoch ends up being slightly higher, but you get training that's almost twice as fast. So the benefit is that you're costing about the same, like it's gonna cost a little bit more, but you're gonna get your models trained a lot faster. And as you scale up to like 16, 32, 64 thousands of nodes kind of thing, your training gets faster and faster, although there are diminishing returns after a while. And then on the right here, this is actually pulled from a paper, and it's an example of the training time that you can expect as a function of the training data set size and the number of nodes in the cluster. So as you can see, you get more or less a 2x speed up each time you scale up by 2x. It's not perfect, but and it's highly dependent on the task. It's not like it's something that you can necessarily guess in advance, but you get generally that. So let's talk a little bit more about the trade-offs here, because it's not a perfect situation where you can just like add more compute and you're good to go. So you have another trade-off between the batch size. So there's this term called the global batch size, which is basically the per GPU batch size, because each GPU has its own batch. So the global batch size is the per GPU batch size times the number of GPUs per node times the number of nodes. So coming back to here, in this situation where you had a world size of 8, if the batch size per GPU was 8, then it would be 8 times 8, which is 64. So what you generally have to do is, to benefit from that distributed training, you have to scale up your batch size, because otherwise you're not benefiting from that parallelism. Because if each node is just processing like one data point at a time, then you're going to spend most of your time doing communication as opposed to actually processing. So when you increase your batch size, you also have to tune your learning rate too. And this is very, very situation dependent. But what I've found from papers and my own experience is that when you increase your batch size by like n or nx, then you should also increase your learning rate by anywhere between the square root of that n or n itself. But it's very situation dependent. And this is important because the batch size can actually reduce your generalization. So if you increase your batch size too much, your model stops being able to specialize for whatever data it's being given, because like each step is just too big. So there's sort of a point of diminishing returns, but I won't get too much into that. And on the right here, you can see a graph where someone has plotted various batch sizes and the learning rate that was required to get the optimal loss. So as you can see here, with a batch size of 4, actually, let's look at the batch size 16. So as you can see, the learning rate is about 10 to the negative 2 at the optimal loss. So the lowest loss is what we want. And the way we got that was with a learning rate of about 10 to the negative 2 for batch size 16 here. But then as you can see, for a batch size of 64, the optimal learning rate is actually a lot closer to 10 to the negative 1. So that's how you have to think about this, is that different learning rates are required for different batch sizes. And then even beyond that, there's like sort of a limit where you just can't push your batch size higher. So how do you actually get your code on distributed training? Well, you generally, for any sort of like Google Cloud, AWS, Azure ML, they provide tools to do this. So you just wrap your training script pass it into whatever tooling they provide, and you're generally good to go. And they'll generally automate a lot of it for you. So with that, let's talk about how to actually tune your compute config. So like you've got your distributed computation going, your distributed training is working, but you're probably wasting a lot of resources at this point, which means that you're wasting money and you're probably wasting time. You don't want to have GPU being sitting idle because it's very expensive. Like GPU instances can be anywhere between like 10 to 100x more expensive than CPU. So you really, really want to tune that. So let's talk about how to do that. So for starters, you always want to begin with a baseline. So what that means is like you always measure where are we right now before we make any changes. And the importance of that is that if you don't measure that baseline, you can't know if any changes you're making are actually improving things. So what do you measure? Well, the GPU utilization is the most important thing because that's the thing you really don't want to be wasting. But you also want to measure CPU and memory consumption too. Once you've got your baseline, you want to tune a variety of factors. So the batch size and the learning rate, as we already talked about, as well as the instance type. So different instance types have different GPUs, different numbers of GPUs, different numbers of CPUs, different tiers of CPU, et cetera. And then you also want to tune the instance count. The instance is, an instance is also another word for a node in your cluster. And then just a couple more tidbits before we move on. Your data loader number of workers you probably want to tune too, because if you're changing your instance type and you have more CPUs, you have more parallelism there as well too. And then when you're doing benchmarks, you don't really care if you get preempted. So you can use what's called low priority compute or spot compute. And that can be helpful just for keeping costs low so that if you're using very large numbers of instances, you're not spending a lot on that. So you might wonder, how do I actually measure my GPU consumption? So there's two main ways to do that. One is that most cloud services will provide some way to do that right out of the box. So on the left here, you can see Google's cloud monitoring for GPU. And as you can see, this measurement, it's hovering around 40 to 60% utilization, which is like, okay, it's not great. It could be better. It depends on the use case though. So there are just some use cases where you actually can't bump it beyond that. But in general, without knowing more, that would not be very good utilization. And then on the right here, if your cloud service doesn't provide that directly, what you could do is there's a tool called NVIDIA SMI, and you can just go in directly to the instance, SSH into it, and then check your utilization with that. And it'll spit out the memory usage on each GPU and the GPU utilization. So this instance has 4 GPUs of the Tesla M40. Its GPU memory is mostly in use, and its GPU utilization is very high. It's like 98% plus. So this is like as good as you can get. Like this is stellar. If you can get this, that's great. And you might even want to scale up your cluster more. So let's say you've measured all these dimensions and you're trying to figure out what do I do based on what I've measured? So first of all, you need to diagnose what's happening. So if both your CPU and GPU are low, there could be many causes for that. So it might be that your batch size is too low, so you're not benefiting from that parallelism you could be. Like if each GPU is just processing one data point, again, that might be too smaller than it could be handling. You might not have enough workers in your data loader. You might have too many nodes in your cluster. Or the saddest, which is it's not very common, but it happens, is that your model might already be at capacity, or it might just be that it's a small model and it doesn't benefit a lot from that parallelism. If your GPU utilization is high, but your CPU is low, that's generally a better place to be because, again, we really don't want to be wasting GPU. But you, again, might just not have enough workers. Like you could be having more workers for your data loaders, or your instance type might be higher on the CPU than it needs to be. So if you use an instance type with lighter CPU, but the same GPU, you might be okay with that too. Over here, where your CPU is high and your GPU is low, this is not a good place to be, but it's still solvable. So your batch size could still be too low. You might have other stuff going on in the background, like online augmentations and stuff like that, that are just chewing through the CPU. Or your instance type might have a heavier GPU than it needs. And last is when both are high, you might just be okay, but you might be also saturating your nodes. So there might be something we could do there too. So what do we do in each of these cases now that we've diagnosed it and we have potential hypotheses for what's going wrong? So if you're low on both, you can increase your batch size. And as we remember before, also increase the learning rate with it. We can increase the number of data loader workers. We could scale down the cluster to fewer nodes or just generally lighter compute for each node. or we could increase our model complexity. If our GPU is high and our CPU is low, then we can still increase our workers and we can switch to an instance type that has a heavier GPU in it. And then the converse is true for high CPU and low GPU. So we'd want to switch to heavier CPU, but we could also increase the batch size and learning rate, or again, in the case of like online augmentations or some other bottleneck like that, optimize our code. Then last is if you're high on both, then you could still increase your instance count until the utilization begins dropping, because it might mean that you could be doing more than you are right now. Last thing I want to talk about, or last major thing, is to actually figure out the optimal compute config. What you generally want to do is you want to build a harness that will grid search across every compute config and then measure the key factors you care about. So there are three main targets you want to pick. So you always start with a metric in mind. What are we optimizing for? So you want to have one or more of three, which is the lowest cost per epoch. So you're measuring the cost in terms of dollar spend per epoch, the training time per epoch, or a balance between the two. And that's because different tasks require different balances of these things. So you want to be able to tell researchers or whoever's training these models, okay, use this one if you want low cost, use this one if you want results quickly, etc. So what you do is you basically build a test harness that grid searches across many different compute configs and measure each of these factors. So you'd change your instance type, you'd change your instance count, and then maybe some other things too, like the number of workers. Measure each of these and then optimize or pick the compute config that hits the right target. So in this table down here, you can see the lowest cost per epoch is this one here, the instance type 1 with node count 1, but its training time is quite high. So we'd pick that for our lowest cost. But then for our lowest training time, we'd look at the training time column and we'd see that row 5 here with GPU instance type 2 and 4 instances has the lowest training time, and we'd pick that, but it's very expensive. And that's why sometimes you'd also pick the best balance too. So you'd pick something sort of in the middle. That there's no exact way to measure that. It's really up to you, but you want to have some kind of balance. Okay, and then just a couple more advanced things. Last thoughts here. You can also do GPU profiling. This is a very advanced technique. I wouldn't generally recommend it unless you're spending a lot of money on this stuff, but you can actually get into the GPUs themselves and understand where your bottlenecks are. You can just Google GPU profiling, and NVIDIA has some tooling for that. You can alter your model architecture, and you can also play around with the way that you're storing your data, such as like using Parquet or HDFS or something like that instead of flat files. So with all that in mind, you now have your fully tuned distributed training config. So congratulations. And if you're interested in solving problems like this, Axon is hiring. So you can check out our jobs board here. We're hiring for positions like senior machine learning engineer, senior research scientist, and a director of product management. And you can contact me directly at dsherk@axon.com. That's it. So it is time for Q&A.
Thank you so much for the great talk, Doug. So we do have time for a couple questions. So if you have your questions, just type in a chat and I'll do my best to get to them. First off, we have a question about it seems that looks like the manually tuning the compute resource can be a time-consuming process. Do cloud computing providers absorb most of this burden? What software tools can help automate this process in the case of an in-house computing platform?
Yeah, that's a very good point. So it depends on what kind of tuning you're talking about here. So for the grid searching, what I found the most helpful is to just write your own wrapper around whatever cloud service is. There's ways to automate it, but it's like, it isn't really helpful because you want to be able to go in and really understand things deeply and play around with different configs yourself. So I found that just having a very thin wrapper around the cloud services, like that table I showed earlier that just showed the instance types and the node counts, getting something like that off the ground only takes about a day or so. And once you have it, it's very general and you can use it for many things. So you could always, have like a job runner, like a worker queue, that kind of stuff if you want to like really scale this up. But for something simple, it makes the most sense to just write something directly for it. And then once you measure the thing that you care about, which is the training time per epoch, then you've got basically the main thing that you want because you can infer everything else from that. Does that answer the question?
Yep, I think that was a pretty comprehensive answer. So I guess the next question is a little bit about, you mentioned that the slide about data parallelism versus ring all reduce. Is there a benefit of using one versus the other, and is there a case for that?
So sorry, was the question between ring all reduce versus having like a main node that is coordinating all the nodes?
Yep.
Yeah, that's a very good question. So not all the tools right now actually use ring all reduce because it's a substantially more complex thing to implement. It is like everything's moving in that direction because it's generally better once you've automated it. But there is a use case for having one sort of master coordinating node. And that's that it's just like much simpler to build and keep track of what's happening. So if you want simpler and you just want to get something off the ground and you're not using an off-the-shelf tool like a PyTorch Lightning or Horovod. Horovod is another toolkit for doing distributed training like this. If you're not using one of those sort of frameworks that does most of it for you, then it can make more sense to use the master node config versus the ring all reduce. But if you've got everything abstracted away and it's doing it all for you, then the ring all reduce can be better. Another thing to consider too is that the master config has two main drawbacks. So one is that there is the network bottleneck, meaning that if you have one coordinating node, all the other nodes are communicating with it, which introduces a bottleneck. And that gets worse the more you scale the cluster, right? If you're at just a few nodes, that might not be that bad. But as you scale it up, as you're getting into like dozens, hundreds of nodes, it gets really, really bad because you're just going to be waiting most of your time for that. And there's actually a practical limit as to how far that can even go. Mm-hmm. That's one drawback. The other drawback is that it introduces a single point of failure. So if you have ring all reduce, then even if a worker fails, it might theoretically be possible to keep going. I don't know the details about like how that actually works and if anything actually implements that. But the point is that there's less of a single point of failure on that. So it ends up being more robust overall. So that's the main trade-off.
I see. And so I guess this kind of touches on the next question, which is how to handle multiple tasks under this scalable training framework.
What kind of tasks are we talking about? I guess like doing NLP versus computer vision versus different types of computer vision and that sort of stuff. Yeah, that's a good question. So this is very general, and PyTorch Lightning. I'm not a shill for PyTorch Lightning. I just really love it, but it's a very general tool that as long as you can fit whatever use case you've got into that structure, where as I talked about, there's the configuring your optimizers, there's just defining your model, defining your forward pass. As long as you can fit your task into that structure, then PyTorch Lightning will pretty much do everything for you. So, any NLP, computer vision task, anything like that will pretty much fit into it. So it does kind of slow things down initially when you're just prototyping. Maybe you're pulling a repo off GitHub and you just want to use that. But as soon as you're committed to using that model, it generally makes sense to switch it to PyTorch Lightning and using that. So that's one. And then also, because of that structure that it brings, you can also have, you can also benefit sometimes from like an inheritance model that it brings with it. So one of the things that we've experimented with is using inheritance to abstract functionality that is common between different tasks. So what that means is like, say you're doing two tasks that both require the same type of data and you're just making a slight change to it on the tail end before you pass it into your model. So what we would do is we would share that functionality using the inheritance structure that PyTorch Lightning provides and just have like a class on top of that shares that, and then they both use that. So that's another nice benefit of PyTorch Lightning is it encourages structuring your code in a way where sort of the imperative approach that most people use for model training doesn't naturally lend itself to.
I see. And I guess our next question for that is, do you mind sharing strategies of training and scaling deployment of models on the edge for use cases like the Axon body? The models keep getting retrained, I assume. So what is the way to deploy models to the product already on field?
Yeah, that one's a bit of a proprietary thing, so I'm not sure I can talk too much about that. What I can say is there are, and I'm not saying we use these or anything, but there are websites you can find where people sort of manage those edge device deployments for you. A lot of companies do it by hand, so they don't actually use one of those third-party services that do it. There are a lot of considerations that go into that, and that does actually change the nature of this. So one major change that makes is that if you're doing edge devices, then you're more likely to hit capacity constraints, as I talked about in this presentation. Not necessarily, but you're more likely to. So that's a major thing to consider too. And it sort of limits the what you can get out of the distributed computation. But yeah, I don't know if I can talk further than that.
That's perfectly
good question.
Fair. I know there's definitely some confidentiality there. So I guess our last question is, how do you manage GPU workers, scheduling management for different projects or different trainings?
Yeah, that's a very good question. So if you're doing things on the cloud, so this is one of the big benefits of distributed computation too, that I didn't really highlight, is that as soon as you hoist things onto the cloud, you can actually provision whatever instances you want and whatever compute you want for that task and then tear it down after. So the nice thing about that is if you want to run like 10 experiments, then you can just run them all 10 in parallel, wait for their results, and then they should take about the same amount of time. Whereas if you're training on like a workstation, you have to run them one by one and then wait until like all 10 are done. So in terms of the actual scheduling, what you would generally do if you're on the cloud is you just provision whatever you need for the task you want, spin that up, use it for that, and then tear it down when you're done. And there's no real advantage to doing anything beyond that because like GPU, like it doesn't really make sense to have multiple things going on a single node. Generally, you could provision a cluster and then whatever node's in it for whatever you're doing. Focus it on that task, and then when you're done, just tear that whole thing down.
I see. Okay. I guess that's it for. Oh, yep. I guess that's it for the questions. Thank you so much, Doug, for joining us today.
My pleasure. Thanks for having me, and thanks for hosting, Peter.
Thank you, and thank you everyone for joining us as well. Have a great day.